Isomerism occurs when, or should I say, is a phenomenon that occurs when you have the same molecular formula but different structural formula or different arrangements in space or different arrangement of compounds. That's another way you can put it. Different arrangement of compounds, or you say different structure, or you say different. Instead, you're going to have the type of isomerism that occurs in coordination chemistry. So, for example, we have the ionization isomerism. We have the linkage isomerism. We have the hydrates isomerism. I gave you guys this one too.
Yeah.
We have the, which one again? You cannot answer. Ionization, linkage, hydrates, ligand isomerism. What do you? Yes, coordinate isomerism. Then for structural, we have geometrical isomerism, which sometimes always relates to the what's it called? The mirror. What's another word for mirror?
Kyber.
Another word again that starts with P. I cannot remember, but something that has mirror images. Like, P. I don't just remember. OP. Optical isomerism. Yes, optical isomerism. So these are the isomerisms that we have. So we're going to be looking at all of them. So please write it down. So that we'll start with ionization isomerism. Write it down. Let's start with the first one. You see that they are reminding me each of them. So write it down now. And we'll take examples, we'll take questions on it too. So let's go to ionization isomerism. Ionization isomerism occurs, we're writing them, occurs when the ligand in the inner coordination sphere. You see that some English language I'm using here is confusing you. If any English I wrote here now is confusing you, it's because you've not attended my class, or you've not watched the video, or you've not read your book. So put yourself in one category. So occurs when the ligand in the inner coordination sphere has the same charge with the counter ion in the outer coordination sphere. These are the things that are probably confusing you now. Counter ion, inner coordination sphere, outer coordination sphere. Is that what's confusing you? I hope not. Alright, let's go. Let me explain what that means. Let's say you have example MnCl2, PPH3, 2, and let's say NH3, 2. Then we now have Br2, for example. Now, this is a compound. This is a coordination compound. If they now ask you for the isomer of this compound, it will have two isomers. How do I know? Because there's a ligand in the inner coordination sphere, chlorine, that has the same charge as the counter ion in the outer coordination sphere, bromine. So because they have the same charge, it means that they can swap. So that's how they now give the isomerism we're talking about. How will they swap? We'll have Mn, Br, Cl, PPH3. You can't swap all at once, you swap one. NH3, 2. So you now have this, and you have Cl, Br. Another isomer you can have is Mn, Br2, PPH3, 2, NH3, 2, Cl, 2. Press it. Okay. So you now have this. So this is what you can have. This like this. So this is one isomer. This is another isomer. So you can have a question that says, what type of isomerism would the following compound exhibit? Can exhibit what? ionization, isomerism. Give the isomers. Draw the isomers is different from give the isomers. But there are some isomers that you might need to draw. For example, this one you don't need to draw. You just give the isomers. Yes. Because they are the same charge. -1, -1. So they can swap. Another example. Another example can be, let's say, Fe, En2, NO2. Let me just put NO2. But let me put CO3. I just told you how to ask the question. I said they'll say what types of isomerism can this compound exhibit. So let's look at this one now, for example. Are we here?
No.
Please be here.
I'm here, but
You can write later. Wait, you write later. Focus on this first. So this is SO4. SO4 has a charge of -2. This is CO3. CO3 also has a charge of -2. So they can what? Swap. So you can also call that ionization isomerism. That's all. Alright, let's go. The next one is what? Let's avoid 30 minutes. Linkage isomerism. This occurs when there is an ambidentate ligand in the complex. This occurs when there's an ambidentate ligand in the complex. The next question now is, what are ambidentate ligands? Abi? I've told you guys before. Ambidentate ligands are ligands with two donor atoms yet are monodentates. They have two donor atoms, but only one can interact at a time. They are ligands with two donor atoms, yet monodentate ligands. So they have two donor atoms, but only one can interact at a time. Example: we have SCN. SCN is an ambidentate ligand. Why do we say it's an ambidentate ligand? The reason is because sulfur can donate, nitrogen can also donate. The opposite of this guy will be NCS. When sulfur is donating, it is called thiocyanato. But when nitrogen is donating, it's called isothiocyanato. Another example is NO2. When nitrogen is donating, it is called when nitrogen is donating, it is called nitro. When it is ONO, which means oxygen is donating, it is called nitrito. Then another example can be CN. When carbon is donating, it's called cyano. When nitrogen is donating, it is called isocyano. So yes, these are examples of ambidentate ligand. So if you now have a complex like this, then I ask you, what kind of isomerism can this guy exhibit? Look at it. Can exhibit what? Linkage isomerism. How do you know? Because you have an ambidentate ligand. What will be the isomer? They are not the same now. One oxygen, one hydrogen. Two hydrogen, one oxygen. They are not the same. It's the same thing. Okay, coordinate isomerism. This occurs when we have a sort of two complexes. That is a compound with two metal centers and two sets of ligands on each metal. E.g., look at it here. So this example, as you can see, this is a salt with two complexes. It has two metal centers and two sets of ligands, right? So this is an example of coordinate isomerism. What can happen here is that these ligands, let's say the metals, they will switch places. That's basically what happens. The metals will switch places, and that's the isomer. So the isomer will be this. You now have Cu NH3 4 ZnCl4. That's it. So this is an example of a coordinate isomer or coordinate isomerism. So this is how it happens. The next thing that happens is that the ligands will switch metals. That's just ligands will switch metal. So when you have zinc before, you now have copper, which is what you have here. So this is an example. This is what coordinate isomerism is all about. Are we there? It's not hard, nice hard. It's just a very simple thing. If it's only happen when you have two complexes like this together, that's the only time it happens. Ligand isomerism. Ligand isomerism. It occurs when the ligand itself has an isomer. It occurs when the ligand itself has an isomer. It occurs when the ligand itself has an isomer. Example. Let's say for example we have NiCN They use TN to represent it, but what is actually called is propylene diamine. Propylene diamine. Let me write that out. That's CH2, 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 NH2, NH2. You know it's similar to ethylene diamine, but instead it has 3 CH2s. Meanwhile, ethylene diamine has only 2 CH. So it's propylene diamine. So it can either be written like this or it should be written like this. This one now is what? It's a 1, 2, 3. That's 1, 3 diamino propane. Why this one is 1, 2 diamino propane? So you see that the ligand itself already has an isomer. So this is where ligand isomerism comes in. But you barely have questions on this, but you have 15 minutes. This is ligand isomerism. It's not hard. I say when the ligand itself has an isomer, this is a ligand. The name of this ligand is 1,3-diamino propane. It can be written like this and it can also be written like this. When it is written like this, it is now a 1,2-diamino propane.
So that SCN, that one is ligand.
SCN is a ligand, but it's an ambidentate ligand. NCS is not an isomer. It's an ambidentate ligand. So geometrical isomerism talks about ligands having the same molecular formula but different spatial arrangements. Ligands having the same molecular formula, complexes having the same molecular formula but different spatial arrangements. Complexes having the same molecular formula but different spatial arrangements. Formula but different spatial arrangements. Is that clear? Different spatial arrangements. I'm going to first of all focus on the octahedral complexes. For the octahedral complexes, let's look at this together. Now, in octahedral complexes, sometimes we have two types of ligands. Sometimes it can be 3, sometimes it can be 4. Right? So we're going to work on that now. If, for example, we have M is representing the beta, A is representing a particular ligand, and B is representing another ligand. M is the meta, A and B are ligands. If I have 4 A's and 2 B, that's octahedral, right? Right? Yes. If I have 4 A's and 2 B's, that's octahedral. These are the ligands, this is the meta. Are we together? Now, how you rearrange this is this. M A B, B. What do you notice? A is in one side, B is in one side. This is what we call a cis isomer. This is a cis isomer. Now the trans isomer of this will be A, B, trans isomer. Are you seeing it? So B and B are trans of each other, A trans of each other. So this is a trans isomer. That is for A4, B2. We can also have A3, B3. Let me give an example of that. A, B. Are you saying this? Because, first of all, I don't know if I've showed you guys before, that these 4 bonds here, these ones, they are actually on a surface like this. While these 2 are standing perpendicular to it. You know what perpendicular is? Perpendicular. This perpendicular. Perpendicular. So the rest of them are like this. 1, 2, 3, and 4. While the other 2 is 1 and 2. You get what I'm saying? Yes, okay. So this guy now, these 2 are perpendicular. While all these ones are more like equatorial. They are on the same ground there. So these 3 like this together are, if you want to look at it, this guy is perpendicular to this one, this guy is perpendicular to this one. So what I'm trying to say in essence is that this guy is going to be 90 degrees to this, 90 degrees to this. 90 degrees to the one that is here, 90 degrees to the one that is here. Because it's standing. So it's 90 degrees to this one and this one. 90 degrees. That's my point. So because it's 90 degrees, we call it a Ma isomer. So that's meridional. Meridional isomer. No, is it no? Sorry. Far isomer. Yes, facial isomer. Facial isomer because of that 90 degrees. While the other one is like that. Now if you look at this one now, it's looking like as if 2 are opposite of 1, 2 are opposite of 1. If you look at the angle, this one will be 180 to this one, but they will be both the 90 to this guy. That was what happened to this one too. This one is also 180 to this one, but they will be both 90 to each other. So this one is the meridional. That's the Ma isomer. So whenever you have, let's say for example, you have a ligand like this, now let's say FeOH3NH3, like this now for example, you say it can exhibit these types of isomer, such that you have facial isomer and meridional isomer. You now draw it. That's why you have something like this. It's when you have something like this that you can apply this. When you have something like, let's say PPH3 4 and then H2O2, you can apply this one. Because this one is what? 4 and 2. Okay, but this one is 3 and 3. There's also another one where you have MA2, B2, C2, meaning when you have 2, 2, 2 in your ligands. Now this is what you use for that one. What can you notice for these three? A6, C6, B trans. B is opposite each other. A are in the same place, that's cis. C are in the same place, that's cis. B is opposite each other, that's trans. This one now, A is the same place, B is the same place, C is trans. C is the same place, B is the same place, A is trans. This one will give you 6 different isomers. Time notice again. All of them are trans. All of them are opposite each other. That's 1, 2, 3, 4. The fifth one. Now, this particular one is more like a cis. A is in the same place, B is in the same place, like they are facing the same direction, and C is facing the same direction. So this is all of them are cis. This one is all of them are trans. This one is 2 is cis, 1 is trans. That's for these three. The last one will be a mirror image of this guy. So that's the last one, the mirror image. So that's what you have. This is for A2, B2, C2. There's another one again for, let's just write this up first. Yeah, let's go. We want to apply it now. The past question on the group chat, somebody should check it. Somebody should check the past question on the group chat. Yeah, now check it. Don't worry. Question, yeah, section B. Section B is not complete, but okay, yeah, it's there. 4B. That 4B question. What types of isomerism will the following complexes undergo and why? The first one there was PT, PPH3. How many PPH3 is there? Is it 1 or 2? 1. PPH3 will be 1, and then I3, Abi? Yes. Then BR. Yeah, looking at this alone before we go so far. What type of isomerism will this undergo? What type of isomerism? Come on now, don't tell me that you don't listen to what I was saying. Ionization. Bromine and iodine have the same charge.
No.
Bromine and iodine have the same charge. -1, -1. Is that not it? Yes. Bromine and iodine are not halogens. All of them have a charge of -1. So they have the same charge. So the The isomerism that we occur here is ionization. And then how do you draw it? PT, PPH3, I2, BR, then I outside. Finish. That's it. That's the isomer. So they say why? Why is it going to have ionization isomerism? Because bromine and iodine have the same ionic charge. So you have seen it now. It's not hard. Let's be fast. So let's move to the next one. That will be OH2. I like this one. 3. Then Cl3. Then Br2. What type of isomerism can we have here now? Ionization and hydrate. Yes, ionization. Why are we having ionization? Because chlorine and bromine have the same ionic charge. Abi? Why are we having hydrate? Because there's water molecule. If you now want to draw out the isomer, you can also do that. What's the isomer for ionization? For ionization, that would be MO, OH2, 3, Cl2, Br, BrCl, and MO, OH2, 3, Cl1, I mean Br2. Then the last one have what? Cl2. So those are the two isomers that we can have for the ionization. What about the what's it called? The hydrate isomers. The hydrate isomers will be MO, OH2, 2, Abi? Yes. Then bromine will come inside. Then Cl3. They will now have water outside, one bromine outside and one H2O. Then the other isomer will be MO, OH2, just one of that. Then we'll have 2 bromine. Then we have 3 chlorine. Then outside we'll have 2 H2O. So that's that. Wait, give me one marker there. Yeah. From there now. What's another isomerism that this guy can exhibit? Look at it very well. This one. Look at it very well. Are you not noticing that it is M? Show it. It is Ma3B3. So that means it can exhibit geometric isomerism because it is Ma3B3. So what are those isomers going to look like? You now draw it out. MO, OH2, 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 Cl, Cl, Cl. This one will be what? This is the facial, Abi. Then the other one, Abi. Yeah, saying it now. Now take note of something. Another thing that she will tell you to do is to name all of them. Yes, that's why I say learn your naming well. You now hear name each isomer. Draw and name each isomer. So you must be able to name and you must be able to draw. You must be able to name and you must be able to draw. What type of isomerism can this guy exhibit now? He can exhibit linkage, Abi?
Yes.
Why can he exhibit linkage?
Because of the SN.
Because of what? Of an ambidentate ligand. Abi? That's that one, Abi? What again can he exhibit? Hydrate. Hydrate, why? What again? Yes, ionization. This is a charge of -1, this is a charge of -1. So ionization. Any other thing? Geometry. Because it's 2, 2, 2. So you not draw all of this. Now, do you understand it now? I see when we apply it, you understand it. So let's draw the geometry first. This is the geometry. Here you have your SCN, SCN, NH3, NH3, H2O, H2O, Br2. That's one. Mn, SCN, SCN, OH2, OH2, NH3, NH3. If you notice, it is the donor atom that I'm bonding. Okay, I'm taking notes. It's the donor atom that I'm bonding. Oh. It's not N I'm bonding. Oh. Where you going to say As you can see, H2O, the donor atom is O. That's why I'm bonding O. Then this one will be all trans. So this one is a mirror image of this mirror image. So you see it's 1, 2, 3, 4, 5, 6 isomers. Then you can now put your linkage. Linkage isomer. So this is the isomer linkage. Here, sulfur is the one being bonded. Here, nitrogen is the one being bonded. So this is the linkage isomer. Then the aqua, I believe we can do that one. Aqua is just the hydrate isomer. This is the hydrate isomer. That's the hydrate isomer. There's no space, if not, I've also put the ionization isomer. I think I can put it up here. Ionization isomer. So that is the ionization isomer. So we successfully did isomerism, VBT, CFT.
So applying.
No, we're not applying yet too. Then let's first of all Na5B cannot exhibit geometric isomerism.
Because it cannot be 6 and trans.
Where do you have to put it again? That will make it exhibit isomerism. So Na5B1 cannot exhibit geometric isomerism. I've gotten that out of the way back. This is what I said. This is what I said.
What is it? He says Na5. What up is
Geometric isomerism. Where did you go?
You were writing. I was writing.
So you see why I said you do not follow me when you're writing. Alright, Ma6 as well cannot exhibit geometric isomerism.
Because it's just A.
Yes. So let's go to 4. Na2B2.
Yes, it can.
It can. Na2B2 square planar. Trusted mapper. So this is cis and this is what? Trans. Abi? That's for square planar. It was tetrahedral. What do you notice? Mirror image. So for square planar, it will be cis and trans. It will be optical isomers. So it's mirror image. Are you seeing it for yourself? It's mirror image.
Like what is not done?
But for what's it called, for tetrahedra, this will also be this is for tetrahedra NABCD. The way we have NABCD for square pima. The other one was for NABCD.
I checked them.
So there's no tetrahedral of MA to BC.
It will still look like this.
So there's no link.
It's the optical. Tetrahedra mostly give optical. There's no what's it called? Cis and trans.